So we are looking at the binomial theorem notes page. Okay, we're talking about how we can expand. The first three here have you use area model, where you like box method. Okay, so if we want to do x plus y squared, you can put x and y, okay, and then you multiply all of the intersections of columns and rows. And so we end up with x squared, and then we have xy twice, so that's 2xy, and then y squared. Okay, so we end up with this trinomial here as our simplified answer. Okay, then they say, okay, what about x plus y cubed? Okay, and hopefully you tried this. If you're watching this on a video, I want you to try 1 through 3 and then come back to check them. Okay, so we take our answer we got from number 1. We put it here, x squared, 2xy, y squared. And now we're multiplying that by another x plus y, okay, because we're talking about it's cubed. We already got the squared. Now we need to multiply it by x plus y one more time. And we end up with some like terms that we can combine. And so the simplified form ends up as x cubed plus 3x squared y plus 3xy squared plus y cubed. Okay. I'm just showing here the highlighting. Number 4 on here says to highlight like terms that you're combining. That's what the highlighting is if you want to do that. Or you can kind of circle diagonally the ones that you're combining. And underneath in the green is just me showing where this 2 came from. It's because we had 1xy and another 1xy. The 1 plus 1 was the 2. Same thing here. We had 1 and 2 of the x squared y's. And we had 2 and 1 of the xy squareds. All right, and then they say, okay, well, what about if we raise it to the 4th power? So we take this answer of the cubed, okay, and I put it across the top, and I multiply it by another xy. Okay, and so here's my area model filled in. I've highlighted like terms that I'm going to combine when I simplify this, and I end up with x to the 4th plus 4x cubed y plus 6x squared y squared plus xy cubed plus y to the 4th. Is everybody okay with those? Doing the area model? Okay, so if you have a binomial raised to a power greater than 2, more than just squared, you can just keep multiplying it out. Multiply by another binomial, by another one, and like this. You don't have to show it in an area model. You can show it with just distribution of each term of the binomial. But that's what we're doing here. We're showing this is the process when we are raising expanding binomials to a higher degree. Okay, B for number 3 asks, what do you notice about the exponents on x and y in each term? Okay, so if we look at, it doesn't matter which number we look at. So in number 2, okay, this was the binomial to the 3rd power. And if you notice in the first term, there's a 3 as the degree. In the second term, there's a squared and a power of 1. That adds to 3. And then in the next term, there's a power of 1 and a power of 2. That adds to 3. And then the last term, there's a power of 3. If we look at number 3, this binomial was to the 4th power. It's a degree 4. We've got the 4th power. We've got a 3 and 1, a 2 and 2, a 1 and 3, and a 4. So for every term in that simplified form, every term, the sum of the exponents is always the power of that expansion. Okay, so you may have noticed that. Something else you may have noticed is that as the power of x increases each term, or excuse me, decreases, so it's x to the 4th, x cubed, x squared, x, and then there's no x at all. That's like x to the 0, isn't it? Okay. Y is going in the opposite direction. It's increasing in degree. It's y to the 0, y squared, y cubed, y to the 4th. So they're going in opposite order of increase and decrease degree. Does that make sense? Okay, so maybe you noticed one or the other of those. Maybe you noticed both, but I would write both down now if you didn't have them. Part C asks what you notice about the coefficients in terms of the expansions. Okay, so one thing maybe some people noticed is that it is symmetric, the coefficients. If I come back up here and look at the very first one, I've got 1, 2, 1. Okay, for number 2, I've got 1, 3, 3, 1. Here I've got 1, 4, 6, 4, 1. Do y'all see that? That's the coefficient. So it's symmetric, okay? It's highest in the middle. The ends are both ones. Where it's just the x or just the y, the coefficient is just a 1, okay? So you may have noticed that it's symmetric. You may have noticed that it's highest in the middle. You may have noticed that it's 1s on the ends. Any of that is correct. And you may or may not have noticed that the coefficients in one expansion are related to the previous expansion. Let's verify. Yes. John. Go fast. That's not secretary. Okay, sorry about that. Okay. Now I went ahead and answered. I have number 5 here, and you may not have gotten this far. That's okay. It says, which terms in the expansion do not have any like terms? So up here where I highlighted in the area models, so this x squared and this y squared don't have like terms to combine with anything. Here, the x cubed and the y cubed don't. Here, the x to the 4th and the y to the 4th don't, right? So it's the terms that are only x's or only y's. They don't have a like term. There's not another term that's just x's or just y's. And that's because there's only one product in the expansion that includes only the x or only the y. So far, so good? Bless you. So I started to say before I had to answer the phone that the coefficients are related to the previous expansion's coefficients. Does anybody notice a relationship there? Has anybody seen how they're related or anything about them? You may or may not. I'm just curious if anybody does yet. No? Okay. Am I good to flip over to the back? No? Okay. I'll give you, no, you're fine. So if we were to always expand binomials to higher degrees in this fashion, it can get kind of tedious, right? Like it could take a while using area model or just distributing another binomial, another binomial, another binomial over and over again. And you can do it that way. It just takes a little bit of time. Okay, you got to write a lot down. Okay, but what we're going to look at today with binomial theorem is kind of going to be a bit of a shortcut for us. A way to expand these binomials a little quicker, less work. You all good now? And this will be posted too if you need to go back and fill in more, or I can scroll back to it in a little bit for you to fill in the rest. Okay, but let's go ahead and take a look at the back. I know I said I was going to show you a video, and I am, but I'm going to go ahead and talk about, go ahead and answer these other questions first, and then we'll talk about, then we'll show the video clip. All right, so number 6 says, well, let me zoom in on this a bit. It asks, how are the coefficients in the expansion of x plus y to the 4th related to those of x plus y cubed? So I went ahead here and wrote them out. So for the x cubed, the coefficients were 1, 3, 3, 1. For the fourth power, they're 1, 4, 6, 4, 1. Do you see the pattern now that you see them written one on top of the other? Do you see a relationship between 1, 3, 3, 1 and 1, 4, 6, 4, 1? Say that again. Yeah, there is going to be repeating within the line because it's symmetric as you go down the line. But from one line to the next, do you see a relationship? That's it. The 4, the 6, and the 4 are the sums of the lines above them. The 1 and 3 add to 4. The 3 and 3 add to 6. The 3 and 1 add to 4. Y'all see that? Okay. The next line is written because that's helping us with question number 7. Because question number 7 says, well, can you predict the expansion of x plus y to the 5th? Without doing a bunch of work? Can we just write the answer out? And so I went ahead and said, well, if this pattern continues, the next line would be 1, and then the sum of 1 and 4 is 5. The sum of 6 and 4 is 10. 10, 5, 1. So those should be the coefficients for that expansion, right? And then we said that the degree of x decreases by 1 each term, and the degree of y increases by 1 each term, right? So when I write that out, I would have 1 is the first coefficient. I don't have to write an understood 1. Then I would start with x to the 5th, because that's the degree, the highest degree. And then no y, because it's y to the 0. I don't have to write that. And then the next coefficient would be 5, and x would go down a degree, so it's x to the 4th, and y would go up a degree, from y to the 0 to y to the first power. And then my next coefficient would be 10, and x would go down a degree, y would go up, and then 10 again, x goes down a degree, y goes up, and then 5, x goes down a degree, y goes up, and then 1, x goes down a degree, so it's x to the 0, it's not there, and y goes up to the 5th power. Does that make sense? Okay, so my reasoning here of like, here's just me showing that relationship, and then I just put it in words. The terms with only x or y always have a coefficient of 1. So notice it's always starts with a 1 and ends with a 1. There's always a 1 on the ends. Okay, and then the others in between are the sum of the coefficients of the previous expansion. So it just keeps going down the line. You keep adding another line and adding the previous terms. Does that make sense? All right. All right. And then last but not least, 8 it gives us the expansion of x plus y to the 6th power here written out, and wants us to come up with the first 4 terms of x plus y to the 7th. So I'm going to write out just the coefficients, 1, 6, 15, 20, and I only need the first 4 since I only want the first 4 of the next line. Okay, so 1, 6, 15, 20. Okay, I know I'm going to start with a 1, and then if I add those, that would be 7, 21, 35, and I don't need to keep going because it only asked for the first 4 terms. And I know x would start to the 7th power and decrease each term, and y would start to the 0 power, which means it's not there, and then it would increase in degree each term. So there would be the first 4 terms of the 7th degree. Does that make sense? Everybody still good? Okay, and then can you answer part B? What other term in this expansion would have the same coefficient as x to the 5th y squared? What do y'all think? Let's look at some of the previous problems. Some that have the same coefficient. So up here, these that are both 10, it's x3, y2, and x2, y3. Or both that have a coefficient of 5, it's x4y or xy4. Do y'all see a relationship in those that have the same coefficients? So which other term would have the same coefficient as x to the 5th y squared? Yeah, you would switch the degrees. It would be x squared y to the 5th. And in this case, that term, the x to the 5th y squared, has the 21 as the coefficient. If I were to continue this out, the next term would be 35, and then, or actually, the next term, yeah, it would be back to 35 and then back to 21, and that's when we would be up to x to the x down to x squared up to y to the 5th. Kind of cool, right? All right, so now I'm going to show a video. I put the link on It's Learning if you want. I think I may have actually accidentally closed the window, so let me reopen it. Yeah. There is some space in the bottom half. We got to watch a little ad, I think, to start this. But then there's a little space on the bottom half of the back of that page where you can take some notes here if you would like to. Well, let's hope it loads. Make this full screen. I don't know why this isn't going to full screen. Okay, I may have too much going on online. I'm going to try. So if you're watching this on a video, I'm going to go ahead and end the video here. But the link to this video, this YouTube video that I'm about to show, is also on It's Learning, so you can go watch it separately. Okay, so I'm going to stop the recording and then we'll see if we can get it to play.